video is on the big O notation. So the big O notation measures algorithm complexity in terms of speed, time, space, memory. So big O is actually measuring the upper bound, how long it takes for an algorithm to run, how efficient it runs, and how much memory it uses, which is a big factor in most algorithms. Now, I have a statement here. I gave you a bunch of pushing out several examples of big O. Now, if I have a statement like this, x equals 4 plus 3, x equals 4 plus 3, this is a constant, so it's regardless, it's always going to do it once. It's not going through any loop or anything. So since this is a constant, that's big O of 1. So if you get an algorithm with big O of 1, that's really efficient, fast. Now, so that's basically what a constant is. Now, I have another example here. I have a for loop, say I in range, it goes to n, and it's going to print I. So this is going to be done once each time, but this is going to be done n times. So if I take n plus a big O of 1, so I'm going to end up with big O of n. So that means that this print statement is a factor of I. So is a factor of how many times I runs, so it's a factor of n. So n is the determinant factor of how many times we print this. So that's why they call this, this is big O of n. And that's linear, because it's going to go, whatever the value of n is. N is 100, so it's going to do this 100. N is 200, it's going to do it 200. So this is a linear condition here. Next one, I have a statement here. I have a constant, w, which is 50, and then so I have a loop here. This loop says as long as w is greater than 0, so you keep dividing w by 2, and that's the new value. So it's actually you're cutting it in half each time. So you keep dividing it by 2. So that's why, since you divide it by 2, that's log of n. So since it's log of n, that's big O of log of n. And that's logarithmic. Alright, so that's my third concept here. The third one, the fourth one. I have a statement here that says I in range of n. So I'm going to do this n times. I'm going to do this n times because that's part of the loop. And this is a while loop that says as long as x is greater than 0, as long as x is greater than 0, I keep dividing it. So this part of the algorithm is big O log of n. And then the outer loop, which is n, so that's big O of n. So I multiply this out, so I'm going to end up with big O of n log of n. So this is also n logarithmic. That's my third one. Now, the fourth one, the fifth one in this case, I have two nested for loop. I have two nested for loop. For I in range n, for k in range n. So for every n, k is going to go 0 to n. So for every n, k is going to go from 0 to n. So this is like taking n squared times plus n. So if I do this one, this is n squared. So with n, so this is the part that gets executed n times, n squared. So n squared. So this is big O of n squared. So this would take time because you got two nested for loops. So if you had 3 nested for loops, it would have been n cubed. So it depending on, so that would be big O of n cubed. Well, so depending on the number of loops that is nested. So it depends on the on the loop here, because this is a constant and that goes k. Now here's another example. I have a statement P0, I goes from 0 to whatever n is, and it's going to do this line here. So because since I is going to go to n, if I calculate this, P would be k times k plus 1 over 2, so that says that k plus 1 over 2 is greater than n. Now if I factor these out, I'm going to get k squared is greater than n, so therefore k is actually the square root of n. So this is my square root. There's other ones which, because of space here, there is big O of the factorial of n, so n factorial, see? And there's the exponential, so there's several. So this is how you can analyze an algorithm. So to see the efficiency of the algorithm. In terms of how fast it's run, how fast this is going to run, and how much memory it's consuming, and which does improve on the algorithm. And thank you.